All right. So we'll talk about the kidneys. The basic unit is a nephron. There's the nephron. Okay. And so the job of the kidneys is to remove toxic substances from your blood. So there's toxic waste products in the blood that you want to remove. Okay. And the transport process is reverse dialysis. Okay. So the transport process is reverse dialysis. What does that mean? So the concentration of toxins in the blood is lower than in the kidneys, in the nephrons. So you have to use pressure to move the waste products from the blood, higher pressure, which is arterial pressure, to move the waste products from the capillaries into the nephron. Okay, so you're using reverse dialysis. Well, the problem is when the waste products diffuse across, but then you lose good stuff as well. Okay, so if this good stuff's concentration is higher, that'll go out. Water will go out, you lose water and all that. And then you have to reabsorb all of that. Okay, so in trying to get rid of the waste product, you're losing good product as well. And now you have to reabsorb the good product. So let me skip a slide here. Okay, so you see, so by the way, reverse dialysis is also called filtration. Okay, so reverse dialysis is you're moving molecules from a lower concentration region to a higher concentration region. Okay, so there's filtration. So here's the blood vessels, capillaries. You're pushing out waste product from a lower concentration region in the blood to a higher concentration region using pressure. That's filtration. But then you're also pushing out good stuff. So you have to reabsorb the water. See, you pushed out water, sodium, potassium. See, along with urea, which was a waste product, you pushed out water, sodium, potassium, glucose, and so on. So ammonia is waste, and so on. And then you have to spend energy to reabsorb the good stuff. Okay? So in trying to get rid of toxic stuff or waste products, you pushed out good stuff, and then you had to reabsorb the good stuff. Did you guys understand that? So that's the process. Okay. So the transport process is reverse dialysis caused by arterial blood pressure. So the pressure is higher here, okay? And look at this structure, see, so you have lots of room to reabsorb the good stuff. Okay, you've created lots of space to reabsorb the good stuff. Okay. So the substance is filtered out of the blood. Okay, filtration is reverse dialysis. You're moving stuff from a lower concentration to a higher concentration. The filtered out of the bloodstream then move into the drainage tube. There's the drainage tube. And active transport is responsible for much of the reabsorption. Okay, so you are having to spend energy to reabsorb much of the good stuff. Okay. All right, so the net effect of the two-step process of filtration followed by reabsorption, the net effect of the two-step process of filtration. Filtration was moving stuff from lower to higher concentration, followed by reabsorption is to rid the body of waste products while maintaining a proper balance of electrolytes. Okay. By the way, kidney failure can cause high blood pressure. So when your kidneys fail and you're not getting rid of the waste product, okay, so you're not moving stuff from a lower concentration to higher concentration. How does the body react? The body reacts by increasing blood pressure, so you can move the waste product. But the higher pressure can cause problems elsewhere. Okay, so kidney failure can cause high blood pressure. If filtration slows or stops in the glomerulus, the kidney emits a hormone called the renin that causes blood pressure to rise. Okay. So again, if filtration is not happening properly, your body reacts by raising blood pressure. So it can push out the waste products. Any substance that caused increased urine output is called a diuretic. Okay, so you see, here's the problem. See, when you pushed out the good stuff, you have pushed out water as well. Now you want to reabsorb water. To reabsorb water, if the concentration of water is high, it'll return via osmosis. But if you have a substance here which lowers the concentration of water, then the water is hard to be reabsorbed. So any molecule, so diuretics are such molecules. Any substance that causes increased urine output is a diuretic. Some of these work by altering the amount of water reabsorbed in the drainage tube. They penetrate the glomerulus but cannot be reabsorbed in the drainage tube. So a diuretic cannot be reabsorbed. Okay. The presence of such molecules decreases the concentration of water in the tube and its reabsorption, resulting in a great amount of water in the urine. Okay. So a diuretic hinders the reabsorption of water. Okay. So when people have diabetes, one symptoms of diabetes is unusual thirst and frequent urination. Okay. So glucose is a diuretic, and if there's too much glucose, so diabetic victims ineffectively utilize glucose, and its concentration rises in the blood. This in turn causes an excessive amount of glucose to pass through the glomerulus and Bowman's capsule. Okay. So now we'll talk about active transport. Okay, passive transport is when stuff moves from, so this is dialysis, you have a higher concentration here and it moves via diffusion to a lower concentration region. This can be assisted dialysis, so facilitated diffusion. So if this is too slow, you can use molecules that will assist the motion. Okay, so this is facilitated diffusion. But there are times when you have to move, many occasions when you have to move stuff from lower concentration to higher concentration. You could do that with pressure, but if that is not enough, you might have to spend energy. And when you have to spend energy, that is active transport. Okay. Active transport is essential for various physiological processes such as nutrient uptakes. You're taking nutrients, every bit of nutrients you want to absorb, so you're taking them from a lower concentration to a higher concentration. Hormone secretion, so when you have a organ that's secreting hormones, you've secreted plenty of hormones there, but you're still wanting to transport hormones there. And nerve impulse transmission. Okay. So again, active transport, you're spending energy to move stuff from a lower concentration region to a higher concentration region. Okay. So passive transport, which uses kinetic energy and natural entropy of molecules moving. So passive transport, either you're moving stuff from a higher concentration to lower concentration, which will naturally happen. Sometimes you can also, okay. So to move them against a gradient, okay, passive transport, which uses kinetic energy and natural entropy of molecules moving down a gradient. Active transport uses cellular energy. So active transport, you're moving against a concentration gradient and you're using energy. Okay. Okay, so active transport is usually associated with accumulating high concentrations of molecule that the cell needs, such as ions, glucose, and amino acids. Okay, so when you want this high concentration of these material in a cell, you are using active transport. So examples of active transport include the uptake of glucose in the intestines in humans and the uptake of mineral ions in root cells of plants. So the transport processes at the cellular level are diffusion, which is dialysis, another word for that, osmosis, reverse osmosis. Okay. What is reverse osmosis? Reverse osmosis is motion of water from lower concentration to higher concentration, and that happens using pressure. Dialysis, okay, dialysis and diffusion. Dialysis is motion of other molecules than water from higher to lower concentration, and reverse dialysis from lower to higher concentration of other molecules using pressure are all passive in nature. So as long as you're not using energy, then that process is a passive process. Okay? So if movement happens because of concentration gradient or pressure, then it's a passive transport. Okay. Active transport is when you're using energy. Okay. So biological organisms sometimes need to transport some substances from region of lower concentration to higher concentration. Okay. Okay. So sufficiently large back pressure can cause reverse osmosis or reverse dialysis. Okay. However, there are known instances in which substances move in the direction where existing pressure are insufficient to cause reverse osmosis or reverse dialysis. So reverse osmosis is motion of water from low to high concentration. Reverse dialysis is motion of small molecules from lower concentration to higher concentration. So in these instances, active transport must take place. Okay, so when pressure can't move from low to higher concentration, then you use energy, and that's active transport. Okay. Active transport is a very complicated process, and it's not completely understood. Okay. Here are two examples. Okay, the reabsorption phase of kidney in a kidney nephron is one example of active transport. So the reabsorption of a lot of good stuff in the kidneys is an active transport process. You're spending energy to do that. Okay. Okay, so here's a couple of other examples. The red blood cells in your blood, the concentration of sodium in blood plasma is significantly higher than in red blood cells. Okay, so here the plasma concentration of sodium is about 150 milliequivalents per liter, while the sodium concentration within the red blood cells is much lower, about 10 times lower. Okay, so here's your blood vessel, here's the red blood cells. The sodium concentration here is 10 times higher than in the plasma. It's 15 times higher than in here. So sodium wants to go into the red blood cells. And you have to active transport, so you have to keep bringing the sodium out from the red blood cells. Okay, and you're spending energy to do that. The concentration of potassium in red blood cells, okay, so let me make my cell. Sodium concentration is lower and potassium is higher. Okay, and potassium wants to come out, and active transport maintains that it keeps pulling back potassium into the red blood cells. Okay, so active transport maintains Okay. The concentration of potassium in red blood cells is significantly higher than in plasma. Okay, so about 20 times higher. Okay. All right, so again, active transporters, when you're spending energy to move molecules from lower concentration to higher concentration. Okay. All right, now so this is where I've changed all the figures in respiration because the numbers in the diagram in the books were wrong. All right, so you have to reprint these documents or look at them online. Okay, so now the problem is the following. So here's an alveoli inside your lung. Okay. The pressure outside here is always atmospheric pressure, which is constant. Okay, and you saw that to move a fluid in a given direction, if you want to move a liquid or a fluid, you have to have higher pressure here and low pressure here. Okay. The pressure here is not changing. So if you want to move air in and out of your lungs, you have to change the pressure inside and out inside your lungs. If you want to move air into your alveoli, the pressure in the alveoli has to decrease. When you want to breathe out, the pressure in the alveoli has to increase to move the air out. Okay? So what you're doing is the pressure outside is constant. What you're doing is changing the pressure inside the alveoli. Okay? And now we'll figure out how you do that. Okay? Of course, when you breathe in, you all know you're lowering your diaphragm. Okay? When you lower your diaphragm, okay, so here's the equation. This is the ideal gas law, nRT. Okay. What you do is if you increase the temperature is constant, okay, so we're talking about the air in the intrapleural cavity, okay. The amount of gas is constant and temperature is constant. So if you increase the volume, the pressure will decrease. So when you lower your diaphragm, you're increasing the volume of this cavity. The pressure decreases. The pressure there decreases. Okay, so now let's say there's no motion of air. Let's start with that situation. Okay, there's no motion of air, so the pressure here is equal to the pressure here. And there's no motion of air. Okay, look at this. The intrapleural pressure is minus 4 millimeters of mercury. So the pressure here is minus 4 millimeters of mercury. Okay, now we'll talk about gauge pressure. So the pressure here is 0 millimeters of gauge pressure is actual pressure minus atmospheric pressure. So if the pressure is P naught, so the gauge pressure here is 0 millimeters. You want 0 millimeters so that air doesn't move. Okay, 0 millimeters of mercury. Okay, if the intramural pressure is minus 4 millimeters, how do you get 0? Remember, the surface tension in the alveoli creates plus 4 millimeters. We did a problem like this in chapter 6. So the surface tension creates positive pressure. Plus 4 minus 4 is 0, and no air is moving. Now when you want to breathe in, what you do is you expand the space by lowering the diaphragm. This pressure decreases, and then that pressure goes negative. Plus 4 minus 6, let's say, it becomes minus 2, and air will start moving. All right, so I'm going to show that to you in a different slide. I hope you guys understood that. Okay, so here we go. All right, so when you breathe in, you're lowering the diaphragm, and the intrapleural pressure drops from, in the other diagram it said minus 4, but it drops from minus 3 to minus 6. Okay, so let's go back here. See, it drops from there, it's -3, but anyway, it drops to -6, and the pressure here now becomes -2 inside the alveoli, and air will move in. Your alveoli fill up with air. Your alveoli fill up with air, your lungs fill up with air, and so once your lungs fill up with air, and then you exchange, okay, you do the exchange of gases, your alveoli fill up with air, you do the exchange of gases with the capillaries, and now once you've done the exchange, now you're ready to expel the air back. Okay. All right, by the way, so with each breath you breathe in half a liter of air. Half a liter is about, can you hold up your, hello there, can you hold up? That's about how much air you breathe in. Yep. All right, so now, so when you're breathing in, your diaphragm contracts, your chest expands, and remember that you were increasing the volume of the interpleural space. And when you want to exhale, your diaphragm relaxes. Okay, the chest cavity contracts, and so this pressure, interpleural pressure, goes back to -3, okay, or -2. So this pressure goes back to -2. There was more air in there, and that pressure increases, so that pressure increases to, the net pressure increases to +1. And that's what's shown here. So in the alveoli, the intraalveolar pressure increases to +1 mg. Okay, and now you can push air out. All right, so there was a lot said there, okay, but what I want to summarize again, okay, so in the alveoli is what you're changing, the pressure. When you breathe in, you want this pressure inside the alveoli to be less than 0 millimeter, that is gauge pressure. So it needs to be negative, and when you want to breathe out, the pressure needs to be positive. Okay. Okay, so the main job, so the respiratory system, most important function is to oxygenate blood and remove carbon dioxide. Okay, so that's the most important job. It also exchanges heat with the environment by the evaporation of water by forced convection. So when you breathe out, you lose some moisture as well. Okay, and every time 1 gram of moisture is lost, you're sending out 540 calories of heat as well. Okay, so just like when your sweat evaporates, when 1 gram of sweat evaporates, you lose 540 calories of heat. Just like that, when moisture is escaping, when moisture is going out with the breath you take out, you're sending out that much heat. Okay, so heat is usually transferred out of the body by the respiratory system, but if the surrounding temperature, if the outside temperature is greater than your body temperature, then you're breathing in warm air, and then you're bringing in heat as well. But it may bring heat if the surrounding temperature and humidity are high. If humidity is high, then you're not evaporating as much water in your breath. Okay, so let's see if I need to point out anything else. So, okay, during inhalation, the diaphragm contracts. So that's muscle action. during exhalation, your diaphragm relaxes. Okay, so and again, you can see this in the diagram. The diaphragm is contracted; it's become smaller, and when the diaphragm relaxes, it regains its original size. Okay, no muscle action is required during to exhale, but it must be used to. It may be used to speed exhalation by forcibly contracting the rib cage. So you can exhale fast by contracting your rib cage. Okay. All right. This is the interpleural cavity. Now you see that there is a negative pressure here. So if you get injured and if this cavity, this balloon gets punctured, then your lungs will collapse. Okay, or if this gets filled with fluid somehow, your lungs can collapse. Okay, so you need this negative pressure to be able to breathe. Okay, so any injury that allows air into the chest cavity increases pressure to atmospheric pressure. So it'll increase this pressure from -4 millimeters to 0 millimeters atmospheric pressure, and then your lungs will collapse. Your lungs will collapse because the surface tension in the alveoli will add pressure and it'll collapse them. Okay. Any injury that allows air into the chest cavity increases pressure to atmospheric pressure and forces lungs to collapse due to their surface tension. So this is called pneumothorax. Okay, so here's a collapsed lung. Air or fluid in the pleural space. Okay. Air is suctioned out of interthoracic region to remedy severe pneumothorax, although the body can slowly absorb air in less severe cases. Okay, so we now know how to bring in air into the alveoli and then expel air in the alveoli. But when you bring in air, oxygen concentration here is higher than in blood, and oxygen diffuses to the capillaries. Carbon dioxide concentration is higher in the capillaries than in the air, and carbon dioxide diffuses there. So you give it time for that to happen, and once that happens, now you have to expel this air. Okay? There are hundreds of millions of alveoli, each about 200 micrometers thick. The cell is roughly the size of a micrometer, or let's say, so alveoli is about, let's say, 50 to 100 cell big. Okay, so that's how big that is. And has walls about 0.4 micrometer thick. Okay, so diffusion of gases between air in the lungs and blood proceeds in the direction, so oxygen from here to there, from higher to lower concentration, and carbon dioxide from higher to lower concentration in the opposite direction. Okay? By the way, the actual rate of exchange is greatly affected by the presence of hemoglobin in the blood. Hemoglobin has a chemical affinity for oxygen, so it aids, and its presence allows blood to carry far more oxygen than it otherwise could. The rate of exchange also depends on blood acidity. Yeah, so there are other factors that aid the diffusion. For our purposes, it's sufficient to think of gas transfer as if it was a simple diffusion, I guess so. But the body is pretty smart. It does other things to aid diffusion. Okay. So now we'll talk about concentration of gases. Okay. So the atmosphere is essentially, well, the atmosphere is 78% nitrogen, 21% oxygen, and 1% other stuff. Okay. So here's, again, about 20% of the atmosphere is oxygen molecules, So the atmospheric pressure is 760 millimeters of mercury. Okay, 20% of that is 75, 10% is 75. So the pressure of the oxygen is 150 millimeters of mercury. Okay, so in the air you breathe in, the partial pressure of the oxygen is 150 millimeters of mercury. Okay. Now it turns out that inside the lungs, in the alveoli, because every time you breathe in air, you don't expel all of the air. So there's some used air in there. Okay. In your lungs, the partial pressure of oxygen is 105 millimeters of mercury. In the blood, the partial pressure is 40 millimeters of mercury. So you see the concentration in alveoli is much higher than in the blood. And oxygen diffuses from alveoli to the lungs, to the capillaries. Okay? The partial pressure of oxygen in the lungs is only 105 millimeters of mercury and not 150, because air in the lungs is only partially replaced with each breath. Okay? The partial pressure of carbon dioxide in the lungs is greater than in the atmosphere. Okay, so partial pressure of carbon dioxide, this should be in the blood. Okay, so blood in the capillaries is greater than in the atmosphere, and so partial pressure of carbon dioxide here is higher than in the air here, and so carbon dioxide diffuses across. Yep. Okay, so that's all right. That ends this chapter, and like I said, I am